Hi, Mr. Hertz, AP Physics 2, Period 1. I'm Panine, and that's Shub, that's Cameron, and today we would like to advertise this amazing telescope with our bare hands and blood, sweat, and tears. So, let's get it! Yeah!
Step 1 is gathering supplies. Step 2 is construction.
Dang it.
Step 3 is assembly.
For the Magnus telescope, our group used a Pringles tube which slides over a mailing tube with a slightly smaller diameter. We placed an eyepiece lens using the bigger magnifying glass at one end and the objective lens using the smaller magnifying glass on the other. The tubes are adjustable, meaning they can slide over each other, allowing the viewer to adjust their focus on different objects.
Mr. Desai, I see you cheating over there. Mr. Diao, I just don't know how to do this integration problem. I keep getting it wrong.
Well, sir, do you see the C?
What's C? I don't see my glass. I don't have my glasses.
Oh, use this then.
Oh, I forgot the C.
Dear Brotherhood, Julie and I are now your newest and most dedicated members to this organization. We have been indoctrinated by your most top official, and we are willing to strike at the very heart of Big Brother in his corrupt nation. I pray that I am not being spied upon right now. Signing off, Winston.
The state is equipped with various outstanding surveillance facilities to ensure that no individual is capable of plotting against Big Brother. This foolish gentleman does not know that he is being watched currently.
Ha, I got you.
The history of the Keplerian telescope. Inspired by the telescope designed and built by Galileo Galilei in 1609, Johannes Kepler set out to create his own improved version of the Galilean telescope in 1611. Each telescope has two lenses on each end, an objective lens and an eyepiece lens. Galileo used a convergent or plano-convex objective lens and a divergent or plano-concave eyepiece lens. While Galileo's telescope had an unprecedented magnification of 30 times, it had one major drawback: its narrow field of view, which often produced a blurry, unclear image for the viewer. Kepler fixed this problem by using a convergent or plano-convex lens for the eyepiece, instead of the concave lens used by Galileo. The advantage of the arrangement is that the rays of light emerging from the eyepiece are converging. This allows for a much wider and more illuminated field of view and a greater eye relief, even though the image appears to be inverted. Moreover, considerably high magnifications can be attained in a Keplerian telescope, thus making it very useful in studying long-distance objects. So, how does our Keplerian telescope work? We use magnifying glasses which have convex lenses for both the eyepiece lens and the objective lens of our Keplerian telescope. The objective magnifying glass lens focuses the object just beyond the focal point of the second magnifying glass lens, the eyepiece. This creates a real inverted magnified image of the object between the two lenses. The inverted image is then magnified by the second magnifying glass as shown. The resulting magnified image means that the field of view that is significantly increased compared to a Galilean telescope. And now, the applications of a Keplerian telescope. Due to their high magnification and wide field of view, Keplerian telescopes find massive applicability in studying astronomy. One of NASA's most notable missions currently is the Kepler mission, which is dedicated to finding habitable planets outside of our solar system, which are of similar size to Earth. The mission uses NASA's Kepler Space Telescope, which has helped us discover 2,342 exoplanets since its launch in 2009.
Hey Puneet, look at the moon!
What? I can't see it. I don't have a telescope. What? Where did this come from? Oh, hey!